All right, welcome to 4.3 or 4-3 parent graphs and their transformations. Mostly what we're doing in this video is going over the parent graphs, and then we'll do a couple of examples of transformations. For some of those transformations and why they work, I would check back to 4-1 when we did the parabolas. So first off, we are going to kind of review how the graph of 3 times x plus 6 squared minus 4 is different from y equals x squared. So in our parent graph, which is the y equals x squared, we have a vertex at 0, 0. We go out 1 and up 1 in both directions, out 1 and up 3. Any parent graph, or sorry, any parabola with an a of 1 will have that pattern. So we have a change in a, so a equals 3. Change in h is negative 6. Remember, h is always the opposite of what you think it's going to be, and k is equal to negative 4. So our new parabola is now going to have a vertex at the point negative 6, negative 4. So we're going to put that over negative 6, negative 4, or at least approximate it where that would be. And then our a value, that is going to take it, instead of going out 1 and up 1, we're going to go out 1 and up 3. So that's going to go out, up 3 in both directions because parabolas are symmetric. And then where we'd usually go out 1 and up 3, so out 1, up 1, out 1, up 3. Now we're going to multiply that 3 by 3 as well, and we're going to go out 1 and then up 9, however that is without a grid, and make our really squiggly parabola. So we're going to look at different parent graphs today. This one is quadratic. That parabola is a quadratic equation. So we're going to be dealing with several different ones today. In class, we did an investigation that kind of went through several of these. The first two are old ones, linear and parabola. With the linear, we have a times x minus h plus k. H and k in this particular case are any point on the graph. Any of these, this is actually the point slope equation. A is our slope. We're not going to talk much about the domain and range today. Quadratic equation, that's a parabola. If we're on a test, the points that I expect you to graph are right there. So minimum of 3, but I would say do 5 if they fit. So if we end up having an a value that's like 3 or 5 or something like that, it may be that these last 2 points go off the grid, and that's fine. Just make sure you get the good general shape. But specify where these points are, because on a graph, if you're just going through grid lines, it's really hard grading-wise for me to tell that you knew exactly where they were. I want to clarify what the vertex is. HK is our vertex. This is our vertex right here. That's our HK point. That is the minimum, the lowest point on a graph if it's opening up. If it's opening down, it's going to be our maximum, that highest point on the graph. So the range is from k, so whatever this is, to infinity. Now, if a flips our parabola over, so it's like that, then it would be negative infinity up to k. Absolute value, and this is what you did the investigation on in class, would be, so absolute value is distance from 0. So if I'm at 1, my y value is 1. If I'm at 2, my y value is 2. If I'm at negative 1, the absolute value of negative 1 is positive 1. Negative 2 is positive 2. So that's why this graph has that look. This right here, 0, 0 on the parent graph, is your HK. Many may call that a vertex. Again, it's your lowest, it's your minimum if it's opening up, your maximum if it's opening down. On that one, I would expect those points to be shown. Cubic, anything to the third power, so multiplied by itself 3 times. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. Negative 1 times negative 1 times negative 1 is negative 1. Now, if we go more out, where we lose a little bit of space there, if I go out 2, 2 times 2 times 2 is 8. So this down here, where we run out of space, this point down here, let me go from the, sorry, from the locator point back to, that's going to be down at -8. So once again, in terms of what you can show, these, wow, whoops, wrong function. This point and this point probably won't both fit on your graph, but try to get one of them on there so you can get a general shape. Otherwise, it's the points in pink that are important. This right here, that's our HK, that's called the point of inflection. Square root, or radical, is the number times itself gives you that number. So we don't have any values over here in the negatives because -1, if you try to take the square root of -1, you don't get a real number. Just take the square root of 0, you get 0. Square root of 1 is 1. The next number up that has a perfect square root, or has a whole number square root, is 4. Square root of 4 is 2. Out would be square root of 9 is 3. So it doesn't start until you get here. So the points I would expect to show are those 3. That is your HK. How you choose to describe that is kind of up to you. It's kind of the side, it's kind of the, I don't know, the vertex of the sideways parabola, I guess you could say. One thing I do want to point out is so far all of our parent graphs, and this continues to be true until we get to the log and exponential, all of our parent graphs go from the locator point, they go right 1 and up 1, every single one, right 1 and up 1, and there's another point. The rest of the graph, you kind of have to figure out the patterns yourself and apply those. Cube root is what times itself 3 times, gives us that number. So if we look back at the cubic, we have the points 0, 0, 1, 1, and -1, -1. So cube root, oh, wrong color. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of -1 is -1. But now we go all the way out here to 8, because the next thing that has a perfect cube root is 8. This would be the point 82 on the parent graph. And this out here would be the point -8, -2. So again, these last 2 points are probably not going to fit on your graph, and that's fine, but try to get one of them in there because the cube root has these 3 points in common with the cubic. So having that final direction, whether it's going side to side or up and down, is really important. Again, that point right there, that HK, that's our point of inflection. Finally, we need to talk about symmetry over the y-axis, which means we have an even function. So a parabola, that's really icky. So here's my y-axis. A parabola, oh goodness gracious, it's terrible. There we go. For every point on this side, there's a point on the other side. So they mirror each other perfectly. So if you were to fold this down the y-axis right here, it would be exactly the same on both sides. Now, that's true for the parent graph of the parabola, but if I were to move it over, then it's not an even function anymore because it's not symmetric at the y-axis. Algebraically, this means, I'm not going to get into it too much, if we plug in -x for x, we get the same thing. Let me cover that at another time, but not today. Symmetry around the origin means we have an odd function, and what that means is that if I have a cubic, for example, if I have a point 1, 1 over here, I also have a point -1, -1 over here. So anything that I have for an xy on one side, I have for a -x, -y. So you have to be able to spin it. So trying to figure out if I can show that to you. Well, kind of. Might look a little bit odd. But if I spin it 180 degrees, this still starts low, goes through the origin, goes up. So if I look at that again, not with that. Try to turn it all the way back around. Motion sickness, anybody? So now that I'm back around, this starts low, goes up high. It's increasing the entire time, but in terms of like left to right, that's what makes it an odd function, that you can spin it 180 degrees around the origin and it'll stay put. Again, cube root and linear and cubic, those are all rotationally symmetric about the origin for the parent graph. If we start moving them over and up and things like that, that changes the situation. All right, so just a couple of examples. Our parent graph that we're dealing with here, because of those two lines, is the absolute value. So what that means is my original, I'm going to do this just a little, okay, now it's not going to let me do it at all. Ugh. I'm going to go out one and up one in both directions. So that's what my parent graph looks like. But a couple of things have happened. One, I have a negative out front, which means my A is -1. I also have change in H and a change in K. So my HK point is now, or my locator point is now -3, -5. So I'm going to take the point, -3, -5, and graph it. Again, normally I would have, going to let me grab that? Nope, not going to let me grab that. We won't worry about it. So normally I would have gone up in both directions, but I'm going to undo that because of this negative. Instead, I'm going to go down in both directions, over one, out one and over one. So remember, we took some notes a few days ago on what A tells us. And A tells us when we go over 1 from the locator point, it tells us what to do. Because A is -1, we're going to go down 1. That's true for all of our parent graphs except for the log and exponential. And you have to be careful beyond that first point. So over 1, down 1 because of the negative. Beyond that, you have to make some careful thoughts about what goes next. Final one we have here is a cubic, and then we'll be done. So we have, again, an A equals -1 and an HK of 3, 5. Sorry, -3, 5. So that means I'm going to go to the point, -3, -5. Because my A tells me what to do when I go over right 1, I'm going to go down 1 because my A is -1. Now I have to build the rest of the cubic around that. So let's remember what the cubic looked like. We had 0, 0, -1, -1, +1, +1, and 2, 8. And then -2, -8. So this was our original. Basically what we need to do is flip that over. And so these 3 points here are going to be, this will move from down here, and this will move to up here. So we need to do that all around my locator point here. So there was my -3, -5. I went over 1 and down 1, so I'm also going to go back 1 and up 1. That's going to be right there. From here, I'm also going to go back 2 and up 8 to get that third point on there. When I say back 2, I'm going from my locator point with the cubic. You don't have to do that. You can go back in 7, but for some reason I need to go from the locator point on my cubics. And that's the cubic. So it's one of those lovely things that just takes some practice. We're going to be doing the same thing with some logs and exponentials in a couple of sections. And that's that for transforming parent graphs.